Okay, now we'll discuss the some more aspects on moment distribution method. I have given you many aspects of how we should complete the given question in 20 or 30 seconds time or by inspection itself, like that. Some more shortcut methods we'll see in the moment distribution method. Now we take the advantage of symmetry of the beam or frame and we simplify the MDM process. Let us see how we have to make it. Shortcut methods in moment distribution method. By taking the advantage of symmetry, we'll take the advantage of symmetry and simplify. Advantage of symmetry means in the analysis of trusses by method of sections, I have given you one point. The same thing was there in strength of materials also. If a beam, a simply supported beam is symmetrical, means symmetrically loaded, say, your shear force, your bend moment diagram, deflection profiles, everything are symmetrical, reactions are symmetrical. So from that, in the trusses, what we have done, any truss is there, if the truss is symmetrical, loading is symmetrical, then member forces also will be symmetrical. Then such cases, only half the frame, half the beam or half of the truss, if you analyze, whatever member forces you get it, just with opposite sign or with the same sign, you can show on the other side. Same member forces must exist. Just when you fold it, they must match. That is called the symmetry means. Here also, if you have a continuous beam, let us say, or frame, where which is symmetrical about an axis, then with respect to that axis, forces on the left side, force on the right side also must be symmetrical. Mirror reflection must be there. So in the process, what we do is instead of solving entire frame and or beam and waste our time, we take only half of the structure and complete the problem in our specified 30 or 40 seconds time. Initially it looks so big a problem, but we still can complete in 40 seconds maximum. Okay, so we'll take first two possibilities can exist. If you have a continuous beam or frame, say, the axis of symmetry can pass through the midspan or it can pass through the support. If at all the axis of symmetry passes through the midspan, then what we do is remove that disturbed span, replace it with another beam whose stiffness is half of the original beam or original member. Then carry out moment distribution only for half of the frame or beam. Whatever moments you get with opposite sign, you write on the other half of the beam or frame. Why with opposite sign is if left side anti-clockwise is there, say, when I fold it, it becomes clockwise. So with opposite sign, if you write it, mirror reflection matches. That's the meaning of that. With opposite sign, we should write all the moments on the other half of the beam or frame. So two cases will solve. First concept is this one. If a continuous beam or frame is symmetrical about an axis, passing through midspan, then consider the stiffness of central span, as half of its original value. as half of its original value. Why should we take half of its original value? Once the fundamental is over, we will prove it. What exactly is happening in this one? Why we are taking half of the original value? Half of the original value and carry out moment distribution for half of the beam or frame. For half of the beam or frame only. Next, with opposite sign, write the moments on the other half of the beam. On the other half of the beam or frame. Now, what is the meaning of this one? Example, first one, we will take one beam, let us say. Assume that we have a continuous beam like this. Subjected to some UDL here, central point load W, some UDL, something like this is there, say A, B, C, D. Okay. Now, the axis of symmetry is here. This beam is symmetrical about an axis passing through midspan. This is YY axis and this is your axis of symmetry. If axis of symmetry passing through midspan like this, then consider stiffness of central span as half of the original value. For this beam, stiffness of BC is KBC and this is KBA. Now what we do is, we cut this beam, this BC span itself, we remove it, replace it with another beam like this. This point, let us say A, B, and that BC span altogether we remove it. This is some independent member. A separate member we attach it with half of the original value, half KBC. This is KBA. This we don't disturb because span is not disturbed. This is the disturbed disturbed part of the structure. So what we do is, completely that BC will cut here, at B will cut it, throw it out. Attach a fresh piece like this. A beam with BC dash is not, whose length is not equal to half. The length is different. I value of the BC dash is also different, such that the stiffness I by L value is half of the original beam. BC continuity is there here. So when you, whatever KBC is there, I by L, that we take it a half of I by L, we write it. Okay. Why we should take half of KBC only? We will see in the proof part of it, because proof of that is required. Then only you will know what exactly is happening here. This is an imaginary beam, ABC dash. You will calculate the fixed end moments due to applied loads on the original beam only. This imaginary beam, you will use it only during the end moment distribution and nowhere else. That equivalence, this beam is equal to an imaginary beam, is valid only when you are dealing with end moments, that's all, nowhere else. This is your imaginary beam. C dash is an imaginary fixed support. We don't deal with C dash at all. Here only we distribute the moments. That's all. Work will be over quickly. within 20-30 seconds you can complete the problem if you take the advantage of symmetry. In the process, if at all the axis of symmetry passes through midspan of a beam, that span you have to pluck it out, keep a fresh part of the beam such that its stiffness is half of kbc. This is now imaginary fixed support. You distribute whatever end moment you are getting, kba, kbc, whatever end moment is there, you distribute that end moment in the ratio of their distribution factors. Only during the distribution of the end moments only you can replace like this half of kbc, because when you are deriving the proof for this, that proof is valid only when you are dealing with the end moments, nowhere else. Okay, so this is imaginary beam. Next, second point is, supposing that you have a frame, let us say, assume that we have a frame like this, subjected to some UDL here, some loading was there, A, B, C, D. Now here you have, this is again the axis of symmetry, YY. This is axis of symmetry. So because it has one axis of symmetry, original beam KBC is the stiffness. At B, original stiffness of column is KBA. Because your axis of symmetry is cutting this beam at the midspan, remove BC completely, replace it with another beam whose stiffness is half of the original stiffness. Not length is half of the original length. Length we change, I value we change, such that stiffness is half of the original member. That means your imaginary frame looks now like this: A, B, C dash. Now this stiffness, this BC dash length is not half of the original length, stiffness is half of the original length. This is KBC by 2, this is KBA. This is your imaginary frame. Imaginary frame. Again, C dash is an imaginary fixed support. Here also you calculate the fixed end moments due to applied load from the original frame. Then distribution factors and end moment distribution you will do for the imaginary frame. Whatever moments you get at A and B, same moments with opposite sign you write at C and D. C dash you don't deal with that at all, because we don't want to deal with the C dash. We wanted at A, B, C and D. C dash is some other frame, some other fixed support. Okay. Next, third point is, supposing that if you have a box frame like this, this is a box frame subjected to some point load W, subjected to upward UDL, say like this. This point, let us say A, B, C, D. Okay. This frame is a box frame. Where we use box frames, they are like tunnels. Supposing that you are constructing a tunnel whose length is say 1 kilometer. So 1 meter width of the tunnel you will take it. Dimensions are like this. In this perpendicular direction you will take unit width, 1 meter width. You analyze only that frame. Whatever moments you get at A, B, C, D, whatever moments you get it, for that moment you provide the reinforcement. We know how to provide reinforcement for positive end moment, negative end moment. RCC you have studied. If it changes from positive end moment to negative end moment, you have to bend the reinforcement. Bending of bars are there. So that reinforcing details and all we give it. For 1 meter, whatever reinforcement details you give it. For 1 kilometer length also same reinforcement you have to repeat. So we analyze generally, like your two-way reinforced slabs are there, say 1 meter width you take and analyze, and you extend whatever reinforcement is there, full length of the slab you will provide. Same thing here. This is a tunnel, maybe you can take like that, it is resting on the ground. This is upward soil pressure. uniformly distributed. Downward there may be point load or there may be UDL also, whatever may be the type of loading. Okay, so this one box frame you have taken. It can be water tanks also resting on the ground. Such cases this will not be there. It is filled with water, let us say. Then water pressure distribution we know. It varies, triangular, linear variation. So with that pressure distribution, you can find fixed end moments at A, B and CD because it's symmetrical about half the axis, say, then cut it, analyze only half the frame. So either water tanks or tunnels are designed, they are treated as box frames. Okay, and you analyze them like this by MDM. This is say y axis. This is your axis of symmetry. So what we do is we'll cut here, take only this much. Because of this reason, you will take only half the frame like this. This point say A, B dash, D, C dash. This AB is KAB by 2. Half of the frame you have to, this KAD you have to take here as it is. Here KDC by 2. This is again KDA as it is. DA DC by 2. AD AB by 2. This is your imaginary frame. In this case, B dash and C dash are imaginary fixed supports. Okay, like this. So, if a box frame is symmetrical about only one axis, then consider only half of the frame with the relative stiffnesses. Relative stiffnesses as shown in figure, and carry out moment distribution for half of the frame only. Now supposing that if you get at this point MAB, you get say clockwise plus 10 kilonewton meter. When I fold it, if this is plus 10 means when I fold it, this will become anti-clockwise like that. That's why it becomes automatically with opposite sign you have to write. With opposite sign, write the moments on the other half of the frame. Now supposing that if this box frame is symmetrical about x-axis also, then you can take only 1/4 of the frame and take moment distribution only at one joint. With opposite sign you can write here, opposite sign here, opposite sign here, you write it sufficient. So that is the fourth case. We'll see now that fourth case. This I remove. Now supposing that fourth example, we have a box frame which is symmetrical about both the axes. Some load W here, W this point, let us say A, B, CD. Okay, this is a frame subjected to some load on the column, some horizontal load was there, let us say. It is symmetrical about y-axis, symmetrical about x-axis also. If I take like this, x-axis, this is your axis of symmetry. This is also axis of symmetry. Because it is symmetrical about y-axis, cut here, throw that half piece out. Because it is symmetrical about x-axis, cut here, throw that piece out. You will get a small piece like this. And now your imaginary frame looks like this. Now remember, this is length is not equal to half of the original column. Then I value is also different from that, and these are different. But I by L value is half of the original frame. This AB is this point, let us say A, B dash, D dash. At A, the stiffness I will take KAB is the original frame stiffness, KAB by 2 we will take it. Here KAD by 2. With these two relative stiffnesses, whatever fixed end moments are there, those end moments we will distribute in the ratio of these distribution factors. Only that end moment we will distribute. When you are calculating the due to load the fixed end moments, this frame we don't use, because further loads, this frame and this frame are not identical. Only for end moments they are identical. Okay, means deflection profiles, we want to get identical profiles, so you can use this way only when moments are applied. This is your imaginary frame. We will see why only end moments it is applicable, because we derive only for the end moments. Imaginary frame B dash and D dash are imaginary fixed supports. Okay, so your conclusion: if box frame is symmetrical about x and y axis, then consider only 1/4 of the frame with relative stiffnesses as shown in figure, and carry out moment distribution. Only this one, you see, carry out moment distribution at one joint only with opposite sign write the moments at all other joints. At all other joints. Now we want to see why we should take half of the original stiffness. In these 4 cases we have taken, now we will see why should we take like that. Now let us see the explanation part of it. Assume that we have a beam like this. Okay. This point, let us say A, B, C, D, subjected to some UDL. Now, it has, this is the axis of symmetry. I have removed the load here deliberately, but if you want to fix the load also, we can keep the load. But if load is not there, deflection profile we can draw properly. Only for that sake, I removed the load, because anyhow we don't want to deal with the loads, we want to deal with the end moments only. Now, this one, if we see the deflection profile, slope is 0, goes up, it bulges out. This is the profile, here slope is 0. Slope is 0 because of the fixed support. So, this is the deflection profile. Now, at this point, if you drop a tangent like this, there will exist some slope. This is theta BC. Theta B also we can write it. Theta BC, theta BA, they must be same. Here also if you drop a tangent, this slope, let us say theta CB. Because loading is symmetrical, deflection profile, support reactions, moments, everything must be symmetrical. That's what you have learned in strength of materials and also in the truss chapter also. So we know that your MBA here, MBC here must be say like this is there, say. This you call it as a MBA, MBC, MBC, and on this one it is MCB. Then MCB must be equal to MBC because of the symmetry. Theta CB must be equal to theta BC because of the symmetry. And because of the symmetry here, at this point, at the axis of symmetry, slope must be 0. Why slope should be 0? You see, in strength of materials you have studied, you simply supported beam subjected to UDL. Where is the, if it is subjected to UDL, central axis is the axis of symmetry. At that axis of symmetry, deflection is maximum, slope is changing its sign. While changing the slope, its a sign, the slope value how much? 0. That's what you have studied. Same. Now, wherever you have the axis of symmetry, whether the axis of symmetry passes through the midspan or central span, center of the span, at the axis of symmetry, slope of the deflection profile must be 0. Why should it be 0? If it is not 0, when I fold it like this profile will not sit on this one. Why it will not sit? Suppose this type of slope is there here also, let us say. This is something axis of symmetry, let us assume. If axis of symmetry slope like this is there, you see here it's going down, this is going up. When I fold this one, this is downward, this is upward. This will not sit on this one. Those slopes are equal. Okay. So for this one to sit on this one, slope must be 0. Now you see, if I cut here and I fold it, this profile will exactly sit on this one. For it to sit exactly like that, their slope must be 0. So at the axis of symmetry, now you see in the strength of materials all the problems, wherever you have the axis of symmetry, at that point slope was 0 because of this reason. Otherwise deflection profiles will not be symmetrical. At the axis of symmetry, slope must be 0. Otherwise Deflection profile. Deflection profile will not be symmetrical. Okay. Now, some deflection profile was there we are taking. We don't want to deal with the applied loads. We want to deal with the end moments only. This is the case, let us say. Now we want to deal with cut here, here. Take this profile alone. Because no loading, only end moments we want to take it. So if I take the BC span alone, the free body diagram, it looks like this. This actual beam. Continuity also was there, of course, but we are taking only BC span. This BC span length, let us say L, moment of inertia, let us say I. This deflection profile was say something like this. Okay, only this profile we have taken. At this point, this is theta BC. This is also theta BC. Theta CB, but is equal to theta BC only. There is a moment like this, some MBC was there, let us say. Here, there is a moment of MCB, which must be equal to MBC only, because slopes must be same. This is your actual beam. Actual beam deflection profile. Okay. Now, for this one, theta BC we know. It is like a simply supported beam subjected to two end moments. A rigid joint, if you want to remove the rigid joint, make it as a simple support, make a simple support, apply moment. As long as deflection profiles match, then what support they are, you don't have to worry. So, theta BC formula we know from strength of materials, MBC into L by 2EI. This is what you have studied. Now, since I don't want to deal with the other half, I want to deal with only half of that. That means this portion I don't want to discuss. Now, how much beam length and I value I should take so that MBC produces same theta BC? I want to replace it with the another beam like this. I'll fix it here. This is B C dash. Now BC dash length is not L by 2, some L1. Remember that, not L by 2. I value is not I by 2 or 2I, it is simply some I1. But I will apply the same moment on this independent beam, same moment MBC. And this deflection profile is something like this. This we know how it deflects. I want to get same theta BC. Why I want to get, so that whatever moment here it comes, C dash or at this point, I don't want to do other part of this structure. But when I apply a moment, see only moment, not applied loads. When I apply a moment, I must get the same slope. Then as far as the moments are concerned, I can replace this beam with this beam. When end moment, for a given end moment, same slope you are getting, say. Then since you don't deal with this one, whether it is fixed or hinged, you don't have to worry. So this is imaginary beam. Now for this imaginary beam, we know what is theta BC. When far end is fixed, for this profile I told you ML by 4EI. So M is MBC. Length is not L by 2, it is L1 by 4E. I value is not same, it can be different I value. So 4E I1. Okay. Now if the same slopes are equal, let us say, I can replace the beams also, because for a given moment same slope you are getting. So only when moments are applied, these two are equal, not for the applied load. On this beam you apply some central point load, say. On this beam apply central point load. Slopes will never be equal. Nothing will be equal. But only when moment is applied, they will be equal. means the same slope you will get it. To get the same slope, we adjust the I1 and L1 values. So equating both. Equating 1 and 2. What I will get? MBC into L by 2 EI must be equal to MBC into L1 by 4 EI1. So I can write I1 by L1 is equal to, I am reversing it. This is now half of I by L. So I1 by L1 is KBC dash. It's nothing but half of I by L means KBC. Because of the continuity of the beam, moment is also developed, means it is like a rigid joint behavior. So half of I by L we have taken. So when you are dealing with the end moments only, I can take a beam whose stiffness is half of the original beam, then slopes moments are same. Deflection profiles only will match when you are applying the end moments. Equivalence is valid only when you are dealing with the end moments and no other applied loads. Okay, conclusion. BC can be replaced by another beam BC dash whose stiffness is equal to half of original stiffness. This equivalence is valid only when end moments are applied. Not valid for other point loads or UDL, etc. In end moment distribution, you deal with end moments only, not the applied load. Whatever may be the applied load, you take the end moment, those moments you distribute. So only when you are distributing the end moments, you can take this one, nowhere else. Okay. Now, we'll see the numericals, how to solve the problem. So our major time will be wasted only in finding the distribution factors and end moment distribution. If you can save your time there, 90% of the time is saved. So that's how a very big beam or frame is given. You can find the unknowns in within 30 seconds or 1 minute time. Now let us see the numericals. Moment at A is this point, let us say A, B, C, D. There is UDL here, let us say 12 kilonewtons per meter, a point load of 8 kilonewton. Again there is UDL of 12 kilonewtons per meter. The span is, let us say, 4 meters I. This is 2 meters, 4 meters I, 4 meters I. Such problems, if you do it in the regular fashion, it will take 20 minutes time. Within 1 minute only, if you want, you have to take the advantage of the symmetry. If any question either in the gate or in the prelims, such type of continuous beams or frames are given, means in the prelims or gate, it means that the frame or beam must be symmetrical, otherwise they will not give. That means you are expected to know how to solve the symmetrical beams and frames. So this is your axis of symmetry, YY. So if it is symmetrical about this one, what we have to do? AB beam, we have to keep it as it is. This is AB. BC, you have to replace it by an independent member like this. This is, as I have explained to you earlier, A, B, BC dash is a independent beam. We simply attached it whose stiffness is KBC by 2. So that whatever end moment you apply for this one and this one, stiffness is same. KBC by 2, if I write it, same slope for the same moment I will get. KBA as it is. This is your imaginary beam. This you will use it when you are finding the distribution factors and distributing the end moments. That end moments from where you will get? From the applied loads in the actual beam only. Okay. So first problem will solve it completely. Solution. First step. Fixed end moments. This is this for the fixed end moments you have to calculate for the actual beam only. Whatever moments you fixed end moments you get for the actual beam, when you are distributing it on the imaginary beam, you will do it to save the time. So MFAB we know, minus W L square by 12. So minus 16. MFAB. MFBA also we know, plus 16. Then MFBC minus WL by 8. Minus WL by 8 means minus 8 into 4 by 8. So minus 4 kilonewton meter. MFBC. MFCB plus 4. Enough up to here. This CD span, AB span same. We don't have to write them and waste the time in the exam. First problem I have given this one. Second problem onwards, this also you can strike it off. But first problem I am giving completely because we must know what is the process involved in solving the problem. Next, second step. Second step is distribution factors. This you will do for the imaginary beam. Because distribution factors for the imaginary beam, when you are distributing the end moments, they are same, because for the same end moment, same slope you are getting. So stiffnesses are same. Accordingly, we have adjusted the imaginary beam stiffness. So distribution factors. First, only at B is sufficient. Joint, member, K, sigma K. Distribution factors are K by sigma K. Okay. Now only one B member, B we have to take it, B. So BA is one member, another member is BC dash. When you stand at B, look at A, because you are finding the distribution factors at B, means you have to stand at B. Look at the far ends. If far end is fixed, I by L, so I by 4. Standard B, look at C dash. It is half of KBC. Half of KBC is I by 4 again. Original stiffness is I by 4 because it is for a rigid jointed one you have taken. Okay. Rigid jointed deflection profile we have taken because C is not like a simply supported one. It is a continuous beam, so there will exist a moment. A simply supported beam with moment or a simple support with moment behaves like a rigid joint. At rigid joint, reaction is there, moment is there. Simple supported beam, simple support, you have a reaction and moment say, then rigid joint and this are identical as far as the structural behavior is concerned. So, like that we should simplify. So, I by 4 is I by 8. If I by 4, I by 8 is there, difficult for us to simplify because calculators may not be allowed. So, I by 4, if I write it as 2I by 8, if denominator is same, numerators we can add directly. So, 2I plus I, 3I by 8. See that simplification it offers if the denominator is equal. So, this is 2 by 3, this is 1 by 3. For this one you see you don't require any calculator also if you write like this. Then third step, end moment distribution. I will write EMD because in the rough work in the exam you cannot afford to write end moment distribution. In the rough work you don't have to explain the anyone that I am doing end moment distribution. Distribution factors are also same. If you could guess how much the value is, even this also you can skip it. But half of I by L is there, you cannot manage. So we have to spend say 20 or 30 seconds time there, 20 or 30 seconds time here. So 1 minute process must be completed. Finally, time is the most important aspect. Joint. This end moment distribution, this is for imaginary beam. Why for imaginary beam? Because same slope, same moment I get. So both of them are identical when dealing with end moments. So only when you are doing end moment distribution, I can distribute the end moments in the ratio of their distribution factors. Okay, joint. This is A, this is B, and this is C dash. See then distribution factors. At A it is 0 AB member, other one is the fixed one. So if you want to write that fixed support wall, say wall 1 A 0. Also okay. So whatever moment you get, it's a plus 10 kilonewton meter you are getting. Then joint should be in equilibrium. So minus 10 will be taken by the wall. Since you don't deal with wall, so we don't write that minus 10 also. Any joint, whether you take fixed support, anything, equilibrium must satisfy the joint also. At the fixed support also equilibrium must be satisfied. So once we say AB span minus 10, then A wall, should be plus 10. Sum must be 0. Otherwise minus 10 who will give to the beam? To the beam wall only should give. That means on the wall it will act in the reverse direction, opposite direction. So here it is 0, BA it is 2 by 3, BC dash 1 by 3. At C dash it is only imaginary support it is. So we don't have to write anything here. Why we didn't write is because C dash is an imaginary fixed support. Okay. Now you write the fixed end moments. These moments are obtained for the actual beam that we want to distribute. This is minus 16 plus 16 minus 4, nothing. We don't write anything there because at C dash plus 4 is not there. C it is plus 4, but we have cut and thrown it out. So no fixed end moments should be written here because that is only an imaginary support. At that imaginary support, fixed end moment also is not there. So this one. Now to fix the imaginary frame at A, minus 16 is required here. Plus 12 is required to fix the joint B. Nothing is there because ahead we don't do anything there. Now you have to balance this minus 16 because of the fixed it will exist as it is. Now release B. Release B or balance. Both mean the same. Now you see, plus 12 is to fix it. But B joint is not a fixed one. Unnecessarily you fixed it. Since you unnecessarily fixed it, you release that. To fix it plus 12. To release it, you apply minus 12. Lock will be gone. Your joint locking moments are plus 12. Unlocking, if you apply minus 12, the fixed is released, it is now free to rotate. Whatever theta b is there, it will happen. So minus 12 into 2 by 3. So minus 8. So you will get minus 8. Then minus 12 into 1 by 3. You will get minus 4. Like that. Minus 8 minus 4. This is how you will release. Now carry over moment. Is this release means who should release? We only have to go there and apply minus 8. Then whatever you locked it, you unlock it. You only have to unlock it. When you applied minus 8, again here that is a symbolic representation of fixing or locking the joint. You fix it like this is symbolic. Then release. That means you only have to release. So when you release it, half moment is carried over. Anyhow, A is a fixed one. So minus 4 it will come. From here to here minus 2 will go, but C dash imaginary support we don't have to deal with. So you don't have to write, unnecessarily write minus 2, add them, then throw them. Instead of that, without writing also you can throw them. Throwing of giant C is common, C dash. So whether you write or not, how does it matter? So why should we unnecessarily write here and waste our time? So this part we simply leave it. After this nothing is left. So fixed, unlock it, issue closed. Now final end moments. In the exam, in 1 minute or 1.5 minute time, you can do only this much. See, final end moments. This final end moments will be different from fixed end moments. These fixed end moments are the moments required to make the slope 0. But slope is not 0 at other joints. So final end moments will be different. So minus 20, plus 8, minus 8, nothing. Now you see he is asking what is the moment at A. Plus 20 or minus 20 they will not ask you, simply 20. Moment at A is simply 20 kilonewton meter. If they are asking clockwise or anti-clockwise, minus means anti-clockwise. That way also we can write. If they want to be more specific also, we can make it. But 20 is the answer. In 2 minutes time, you have to first see whether it is symmetrical or not. If it is symmetrical, you check whether it is passing through the support or passing through midspan. If it is passing through midspan, remove that span, put it half of the original span stiffness. Then find distribution factors and distribute the end moments for the imaginary frame or beam. When you are distributing it, only one line, only one time balance only is required. Second time also if you are doing the balance, it means that somewhere you have done wrong. If you have to do second time also, it means that you have not taken the advantage of symmetry. That means within 2 minutes time, 2 times balancing impossible. You have to calculate distribution factor, 2 times balance. Then you have to tick that one. All the things overheads will take time in terms of seconds only. So that's why they don't exceed beyond this one. 2 times earlier problem, if you have to do 2 giants distribution, it will take minimum of 6 minutes to 7 minutes time. Then it is a 20 marks question. 2 marks question means only once you have to do, close the problem. Okay. Now let us take one frame. This is a beam you have understood. Now in the next problem, this fixed end moments you don't have to list it for the actual beam. Cut it off. Only these two things we will write from the next problem onwards. Now let us see this one. Moment at B is this point, let us say A, B, C, D, subjected to UDL of say 1 kilonewton per meter. This is 12 meters I, 12 meters I, 12 meters I. Okay. Now you see this frame is symmetrical about y axis. This is your axis of symmetry. So BC you have to remove and replace it with another beam. This we should not disturb. This is another one. This point A, B, C dash. This value is KBC by 2. This we will not disturb KBA. This is your imaginary frame. Now I am skipping the first step. Fixed end moments MFBC minus WL square by 12. 1 into 12 square by 12 is 12. So minus 12 plus 12. Skip it off. We don't have to write also in the exam. So directly start with the second step. In the exam, this is what you have to do it. Distribution factors for imaginary frame. This you have to calculate because you don't know beforehand. You have to spend time. Joint, member, K, sigma K, then distribution factor K by sigma K. Imaginary frame means only one joint you have to take it B. This is BA, BC dash, B to A, BC dash. So BA, far end is hinge. So BA is, I have to write now 3 by 4, I by 12. That means 3I by 48. Then BC dash, half of I by L. Half of I is 12, I by 12. So you will get I by 24. To match this and this, I by 24, I can write 2I by 48. Both are same. So 3 plus 2, 5. 5I by 48. Then this by this means I by 48 common. 3 by 5, 0.6. 2 by 5, 0.4. So in the exam, distribution factors also at the most you have to calculate at one joint only. If you have to calculate at two joints such distribution factors, then problem is gone. That means somewhere something you have not taken care of the observations. Because two joints we have to write and distribute the moments beyond the scope of 2 minutes. So we immediately when you are writing one more joint here say for the distribution factor, stop the work. That is not the way to do the problem. Check for getting out of the problem easily. So that's it. Next, second one, end moment distribution. Here itself we'll write end moment distribution for imaginary frame. Whatever you get it, with opposite sign you have to write for the other half of the frame. Joint A, B, C dash. Here A, B, C dash. Then distribution factors. Here it is 0. BA, you got it 0.6. BC, 0.4. Nothing. Reason is same. Then fixed end moments. See here, if you are confused how that comes, MFAB, you can write if you want. MFBC minus WLB L square by 12. So, minus 12. If you want to know how that minus 12 came, this is the reason, minus 12. So, this is AB is nothing. On the span AB there are no loads, 0 0. MFBC minus 12. CB dash we do not want to write. So, at B, to fix the joint B, you require minus 12 kilonewton meter. That means to lock the joint B, minus 12 you have to apply. Then now you release B is not fixed one, so release it. That means plus 12. When you apply plus 12, when you apply plus 12 on that joint B, that will get distributed, that will be shared by two members in the ratio of their distribution factors. So, plus 12 into 0.6 plus 7.2, that is called balance. So, plus 7.2 plus 12 into 0.4 means plus 4.8. Your 1 minute by this time it will be over. So, 7.2 after carryover moment, all that nonsense, you write it moment at B, you get 7.2 only. Stop the work, 7.2 you take it. But I am assuming that you are learning it for the first time. So, process I am giving, finally moment at B is 7.2 we can write. Now, you see carryover moment. How much is carried over from here to here? 0, because A is a hinge support. Here to here half will be carried over, but we do not want to deal with that C dash. So, we do not send anything up on that. So, over. Now, final end moments. Final end moments. It is 0. You see plus 7 point only you have to write. Naturally, it has to be minus 7.2, nothing. See how much time we wasted? 7.2 you have dropped it. So, moment at B is nothing but 7.2 kilonewton meter. Plus or minus they will not ask you. 7.2 kilonewton meter, like this. So, in 2 minutes time, first you have to identify that it is symmetrical, then half of that imaginary frame you draw for better clarity in the rough work. Two steps should be completed. Now, we will take a third example where a box frame we have to take it. I remove this one. See, in all these examples, axis of symmetry is passing through midspan. Moment at A is. Now, let us see one box frame. This is say 4 kilonewton. 4, this point say A, B, C, D. This is 2 meters I, this is 1 meter. 4 meters I, this is also 4 meters I, 1 meter, 2 meters I. Okay. Now, this box frame is symmetrical about x axis as well as y axis. These two are called axes of symmetry. So, since it is axis of both, two symmetric axes are there, cut here, only this small piece you will get. This is your imaginary frame A, this is B dash, this is D dash. This I have to write KAB by 2, this is KAD by 2. This is your imaginary frame. First step, we will again here also skip it. Then distribution factors. solution. This distribution factors for imaginary frame, joint, member, K, sigma K. Distribution factors are K by sigma K. Only one joint you have to take, A. This will be AB dash, AD dash. Now AB dash is KAB by 2. KAB means half of I by L, half of I by 2. That means it is I by 4. Then this is half of I by 4. That means this is I by 8. So to make two denominators equal, I will write this as 2I by 8. This will become 3I by 8, 2 plus 1, 2 by 3, 0.67, 1 by 3, 0.33. See, no calculator, nothing is required. So now second one is EMD. For imaginary frame. Next time when you are doing this line, you skip it off. You don't have to explain this one to anyone. First time, so I am writing. So only this and this table should be present. After learning these things, you must practice again on your own. Then check the time, how much you are taking. That is important aspect. If you are taking say 2.5 minutes or 3 minutes time, better we don't solve such problems in the exam. Because you are wasting your time. Even if you solve also, somewhere you will lose the marks. That's why I tell you, not only your ability to solve the question, but how quickly you solve the question is also a very, very important aspect. Okay. So, for the imaginary frame, joint, this is A, otherwise joint no. So, you start from one end, B dash A D dash or D dash A B dash, our choice, B dash A D dash. Distribution factors, here nothing, B dash you don't deal, AB dash 0.67, AD dash 0.33, here nothing because they are imaginary fixed supports. So, two times we have written, why unnecessarily write, B dash and D dash are imaginary supports. So, we don't have to show any moments also, no carryover moment to that, only at joint A you distribute the moment, that's all, work will be over. Maximum of 20-30 seconds you can complete. Fixed end moments, AB dash, on AB dash, you see here, this is how it looks like. This is fixed end moments for the actual, this one, A, B. Load is 4 kilonewton. So, when you apply load here to detect how the direction of fixed end moment is, first permit the slope to happen. When I pull it like this, it will deflect like this. Now, to make the slope 0, I have to push him like this, push him like this. So, this is MFAB, clockwise, so plus WL by 8, 4 into L means 2 by 8. So, you will get MFAB as 1. MFAB is WL by 8. So, 8 by 8 means 1 kilonewton meter. So, plus 1 kilonewton meter. B dash we don't write anything. AB dash is plus 1. AD dash, there is no load on the span AD. So, 0, nothing. So, to fix the joint A or to lock joint A, you require plus 1. But A is not a fixed support, so unlock it. Why we should unnecessarily fix it and unlock it is, we know only when you fix it, you know what is the fixed end moment. When you unlock it, how much is carried over, we know. So, from the unknown problem, we convert into a known problem. As I have shown you earlier, a propped cantilever was there, some load is there. Moment at A means you don't know, but when you fix it, you know. First fix it, then release, then we know end moments. Like that. So, balance. When you balance it, minus 1 you have to apply, minus 1 into 0.67, minus 0.67, minus 1 into 0.33 minus 0.33 over from here 0.33 is the answer. One of the options is 0.33. This is extra unnecessary we are writing. From here to here nothing is carried over, nothing is carried over. Now you see final end moments. This is plus 0.33 minus 0.33, nothing. So moment at A is 0.33 kilonewton meter. Okay, like that. Okay, so this is a 2 marks question. In one of the civil services, they asked it as a 20 marks question. There, after finding this one with opposite sign, you have to write all the 4 joints and you have to draw a bending moment diagram also. That means it will take say 4 or 5 minutes time. So that's why 20 marks. 1 minute or 1.5 minute means 2 marks, like that. So one problem we will also show with opposite sign, entire diagram will draw that how the moments opposite sign with opposite sign you have to write on the other half. Now all problems if you write it again problem looks so big, okay, it's not for us. That 1 minute time specification will be lost. So this is about the frame. In the exam any question given means only this much you have to do it. Okay. Anything extra you are doing means you stop the work and again observe the problem. Whatever I told you that how the simplification can be done. Then check for the symmetry or say, so many other simplified shortcut methods I have told that you have to take it. So to get the correct idea, okay, let it take 1 minute time, another 30 seconds you can solve the problems. Okay. So moment 8. Now you have taken for a beam, frame, box frame, where axis of symmetry is passing through midspan. It is not necessary that every time axis of symmetry must pass through the midspan. It can pass through the support also. Here 3 spans, one problem I gave, 4 spans are there, then axis of symmetry cuts the support itself. Such cases where axis of symmetry is passing through a support, at that support deflection is 0, slope should be 0, otherwise deflection profiles will not be symmetrical. That means that symmetrical axis which is passing through the support, you can idealize that as a fixed support because slope is 0, deflection is 0. So, cut other half of that without disturbing, without replacing any relative stiffnesses. As it is, you take half of the beam or frame, analyze it with opposite sign, fold the means with opposite sign write on the other half of the beam or frame. That we see in the second concept. In all these problems, you see fixed end moment, final end moments are different. If fixed end moment, final end moment are same, that means that all slopes are 0 for the, after unlocking also slopes are 0. That is the implied meaning there. That we see in the second concept. If a continuous beam or frame is symmetrical about an axis passing through the support, then consider that support as fixed support. Let support as fixed support and carry out moment distribution for half of the beam or frame. For half of the beam or frame only. No question of changing the relative stiffnesses, because you didn't change the length, you didn't disturb any deflection profile at all. Okay, with opposite sign, write the moments on the other half of the beam. On the other half of the beam or frame. Now, why we didn't disturb the relative stiffnesses? Let us see what it means. Supposing that you have a beam like this, say. Assume that you have UDL here, there is a point load W, again there is a point load W and UDL. This point, let us say A, B, C, D, E. Now, all lengths are same, let us assume I values are same, and this is the axis of symmetry, let us say Y. Axis of symmetry. At the axis of symmetry, because it is passing through the support, deflection is 0. Slope also must be 0. If slope is not 0, deflection profile will not be symmetrical. So, now your deflection profile goes something like this. Here it has to be 0, like this, with 0 slope. Now, at B, slope can exist. It can go up, can go down. Say something like this, okay. These will be always smooth curves. Here also same, it is going down, up. Say like this. So, here theta B can exist. Let there be theta B, but theta C has to be 0. This and this is, say, some theta B will be there. This also theta B, theta BA, theta BC, let us call it as theta B, and that must be same both sides, but theta B can exist. But at this point, theta C must be 0. Supposing that if theta C is not 0, if theta C is not 0, with respect to axis of symmetry, I fold it, then this must sit on this one. If like this is there, say when I fold it, this is downward, this is upward. That situation is here, say when I fold it, one is down, one is up, then it will not be symmetrical. That means it is not a symmetrical problem. Because there is an axis of symmetry, the deflection profile has no choice, it has to be symmetrical. For it to be symmetrical, slope must change its sign, then when you fold it, this will sit on this one. So, whether axis of symmetry passes through the support or through midspan, at that point slope must be 0. At the axis of symmetry, slope must be 0, otherwise deflection profile will not be symmetrical. Same reason, You should. Now you have a fixed support, let us say. Supposing that you have a cantilever beam sub AB. At this point, at A, theta A 0, y A 0, slope is 0, deflection is 0. Same thing is happening, deflection is 0, slope is 0. So, I can idealize this and that as same. Here also slope, if at all due to some point load, it will deflect like this, say. Here deflection is 0, slope is 0. Here also deflection is 0, slope is 0. That means I can cut, throw it out, I can take it as a fixed support. Once deflection profiles match, then corresponding to that we can take it and stick it here. So, now this will cut it. See, we did not disturb any deflection profiles. So, we will keep simply as it is. Your imaginary frame or beam looks like this, that is all. No change of length, nothing. This is A, B, C. This is your imaginary beam. But C is not imaginary support, it is actual support. C is not imaginary support, it is actual support. Since we do not want to do the other half, we will fix it. Whatever moment you get on this one, on the other side with opposite sign will be there. So, analyze only half of the beam or frame with opposite sign right on the other half. So, complete analysis is over, because the end moments have no choice, they have to be also symmetrical. Then why should it be opposite sign? Supposing that you are getting MAB anti-clockwise. With respect to this, if I fold it, that anti-clockwise will become clockwise. When I fold this one, it becomes like this. That is why with opposite sign we have to write. Okay. So, this is when the axis of symmetry passes through the support, we do not replace anything. This is KBC as it is, no KBC by 2, nothing of such sort. This is KBA, no change of, no question of changing any relative stiffness. Yes, as it is, we solve the problem with half of the beam or frame. Okay. Now, let us see how the questions will come. I remove this part and solve the problems, and that problem should not take more than 1 minute time. Whether in gate or here, it will be only, or in the prelims, 1 minute time is the maximum time that you should finish off. First, always keep in mind that I must complete in 1 minute time, which means that I should not think too much, I should not calculate too much. These 2 points if you keep in mind and see the problems, you will know how we should get out of the problems easily. Okay. So, moment at A. Now, let us see one problem like this. This is UDL of say 12 kilonewtons per meter AB. This central load, point load, let us say some 32 kilonewton, 2 meters, 4 meters I. This is 4 meters I. There is again point load here, 32 kilonewton. And UDL is there, say 12 kilonewtons per meter. This is also 4 meters I. A, B, C, D, E. So, we want to find what is the moment at A. Allotted time, let us say 1 minute. So, now quickly by understanding this, though it looks so big, but you should be able to finish off in 1 minute time. First, this is your axis of symmetry. Okay. Now cut, throw that piece out, passing through the support. So we don't want to change the relative values also. So your imaginary beam now looks like this. Okay. This point, let us say A, this is a B, C, actual support. Okay, this is your imaginary beam. Now fixed end moments, if you want to find, 12 into 4 square by 12. So you will get how much? Or imaginary beam distribution factors, let us say. Here distribution factor is 0. Here at B. Actually, for the distribution factors, what I have done in the earlier problems are, we have drawn the table, joint, then member, K, sigma K, because we could not find half of that when you have taken. Half of I by L means how much it is, then you have to simplify. But if you know beforehand how much the values are, then why to write unnecessarily the table and waste our time? Now it is fixed. Okay. Stand at B, look at A, I4, fixed. So distribution factors are 0.5, 0.5. When you can find the distribution factors by inspection itself, don't draw the table also. So directly you can show 0.5, 0.5. Here it is 0. Okay. These are the distribution factors. Okay. Now fixed end moments. How much is the fixed end moments? Here minus WL square by 12 minus 16 plus WL square by 12 plus 16. Then WL by 8, 32 into 4 by 8 means minus 16 plus 16. This is the first step, fixed end moments. Second step is distribution factors. Third step is EMD, end moment distribution. That end moment distribution, when you tried, now what is the moment necessary to lock joint B? A already fixed, C already fixed, so we don't touch them. To lock joint B, how much now moment is? Plus 16 minus 16. That means net moment is already 0. So to lock the joint B, you don't require any moment. That means due to applied loads itself, whatever fixed end moments are there, due to that itself, it is already locked. Locked means theta B is 0. So since the fixed end moments are already balanced, it means that the joints are in equilibrium with those moments itself. You don't have to again distribute. That means your fixed end moment, final end moments are same, which means that slope at A, B, C are 0. If fixed end moment becomes final end moment also, which means that what? The slope must be 0. Otherwise, fixed end final end moments will not be same. So, moment at A minus 16 directly. That's all. In 2 minutes time, your task is only this much, because the fixed end moments are already balanced. You don't have to do again balancing task, already they are balanced. So your fixed end moments will also become final end moments. Okay. So we'll write those points so that you will not forget. This is the first point. Since, we'll write completely, since fixed end moments are already balanced, at B, moment distribution is not required. because this minus 16 in the form of carryover moment also it will not come. So, no carryover moment is there. Fixed end moments are also now will become final end moments because you don't have to touch those values. So, moment distribution is not required. Fixed end moments are also final end moments in this case. Okay, that's the first thing. Like that, if at all fixed end moments are also final end moments, it means that slopes are also 0. That is second point we'll write. If fixed end moments are also final end moments, then it means that slope at that joint is also 0. That is theta b must be 0. Now you see, if theta b is 0, that means theta d is also 0. So due to different reasons, slopes at all the supports are 0. At A, because of the fixity, theta A is 0. Theta B, since no balancing was required, theta B is 0 because fixed end moments are already balanced. So theta B is 0. Theta C is 0 because of the axis of symmetry. Same is the case on the other side. So theta A, theta B, theta C all are 0 due to different reasons. Okay. So now you see how the deflection profile goes. Third point, deflection profile. This point, let us say A, B, C, D, E. Everywhere slopes must be 0. Here profile is something like this, slope is 0, theta C 0, theta D also 0. Now here theta A is also 0 because of the fixed support. Okay. Now so is the case here. So is the case here. So is the case here. Theta A is equal to 0. This is because of fixed support. Theta B 0 because fixed end moments are already balanced. Theta C 0, why? Because of symmetry. Same theta D 0, theta E 0. So due to different reasons, all the slopes are 0. That means if the fixed end moments become the final end moments, let us say, that means that the slopes must be 0. Otherwise, why they will become final end moments also? Fixed end moment means that moment required to make the slope 0. If that happens to be final moment also, it means that slope will have to be 0. like that. Okay. Now let us see next problem. Moment at B. So now I think you have got that clarity. Fixed end moment is different. Final end moment is different. Final end moment means after the completely it is in equilibrium, the moments that it takes after the joints rotate. After joints rotate, then whatever moment you get it is the final end moment. Fixed end moment means moments required to lock it to make the slope 0. What is the moment? Then after unlocking, they get distributed. It will be in equilibrium. Then in the equilibrium condition, what are the end moments? They are called final end moments. Now let us see next question. Moment at B is. We don't have to worry about by seeing the length of the problem. Finally, it will take 1 minute time only, whatever may be the case. This point, let us say, moment at C, you will write A, B, C, D, E, F. This is 6 meters I, 6 meters I, 6 meters I. This is 8 meters 4I, 8 meters 4I. This UDL is. They give you the dimensions also such that you don't require any calculator. Okay. Now the axis of symmetry is here. So this is your axis of symmetry. Axis of symmetry is passing through the support. So we'll fix it. Once you fix it, entire column length, you don't have to fix it and show. Just symbolically fix it here, entire thing you throw it out. So fix it here means the entire column also is like a fixed support. Now it becomes like this. That's all. This point A, B, C only. Since axis of symmetry passing through the support, we should not change any relative stiffnesses at all. A, B, C, lengths, I values, everything as it is. C is not an imaginary support, it is actual support. This is your imaginary frame. C is actual joint or actual support, we can take it, whatever way you want to read it. So first step is fixed end moments. So here I will show that. Only one MFBC is sufficient. First step, MFBC minus W is 24, L square is 8 square by 12. So 12 into 2, 64 into 2 minus 128 kilonewton meter. MFBC minus means MFCB plus 128. Don't have to write. Then second point, distribution factors. For whom? For imaginary frame. This is for actual loading. Okay. So for the imaginary frame, so joint member K, then sigma K, distribution factors are K by sigma K, like this. Only one joint you have to take it. No question of two joints because that much time you will not get. BA, BC. So BA means I by 6, BC means 4I by 8. See, two are different, so convert into same value. 4I by 8, I can write it as I by 2. I by 2, I can write it as 3I by 6. Why so much pain is this denominator is 6. Here it is 8. Make them tally so that you don't require calculator to simplify this one. So 1 plus 3, 4. 4I by 6. So 1 by 4. This is 3 by 4. Okay. So this is your distribution factors. Next, third point is EMD, means end moment distribution for imaginary frame. So again, joint C A, B, C, then distribution factors. Here it is 0 because fixed support. BA 1 by 4, BC 3 by 4, C 0 because it's like a fixed support only. Then fixed end moments. MFAB on the span AB 0 0, BC minus 128, CB plus 128. Because C is a fixed support, we should not release because it can take. The slope is 0 already. This is the moment required to make the slope 0. Already slope is 0. So whatever moment is there, don't unlock it because it's already locked one. But B, to lock it, minus 128 is required, but B is not locked. So unlock it. To fix it, minus 128. To release it, plus 128 you have to apply. That is called balance. So plus 128 into 1 by 4. So you will get plus 32. 32 into 3, 96. Then carry over moment. See, at A half the moment is carried over because it is a fixed support. Out of 32, 16 will come here. Out of 96, half of that, 48, 5 plus 3, 48. Okay. So now net fixed and final end moments we can calculate. After distributing, the moments that you get are called final end moments. This is fixed end moments. Final end moments. It is plus 16, plus 32, minus 32, plus 176. Okay. Now he is asking what is the moment at C. So moment at C is simply 176 kilonewton meter. So in 2 minutes time, it is one of the gate problem. This and this should be finished. Okay. Now at least one problem we will see how the with opposite sign we have to write on the other half of the beam or frame I have told you. So that we'll see here in the process. Moment at C means simply 176 you have written. Now I want to know what is the moment at C in the column CD say. If they ask, then you must answer this way. If the axis of symmetry passes through the column, at that point the slope is 0, which means that columns will never take any moment. If slope is 0 implies that that moment also will be 0 on that. Otherwise, to rotate a member means you require some moment. Okay. So rigid joint. We'll take now the free body diagram. Whatever I discussed, we will see why moment at C for the column CD at the axis of symmetry should always be 0. Now see, next question will write moment at C. in the column CD is. Now I'll draw the diagram. Next problems onwards, you must by inspection should tell that because CD is at the axis of symmetry, in that column moment cannot exist. If moment exists in the column CD, CD column rotates, then symmetry is gone. That's why for it not to rotate means then CD must be vertical. It will be vertical only when moment is 0. Now we'll cut them. Free body diagrams means like this. AB member will cut, BC member will cut. Separately we will draw individual members. This is AB member. Then BC member I'll show here. Then CD member. Then this is one more member. This is another member. All 6 members I am showing. A, B, B, C, 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 D, C, E, E and F. So this is length is 6 meters. This length is 8 meters. 6 meters, 8 meters, 6 meters. Then you have to show the load also. Free body diagram means you must show the applied loads as well as what other members are doing on this one. This load now it is 24 kilonewtons per meter. Here also load is there. 24 kilonewtons per meter. So you have shown on this free body diagram only the applied loads. And what the support will do on this? That end moments also you have to show. For that one, this you have to see. AB member at A, for the member AB plus 16, plus implies that it is clockwise. So you show that clockwise 16 kilonewton meter. This 16 clockwise because it is plus you got it. At A for the member AB plus 16. At A for the member AB is plus 16. Next, this is plus 32 where at B for the member BA. At B for the member BA, this is 32 kilonewton meter. Next, this is minus 32 where at B for the member BC minus 32. At B for the member BC minus 32 means anti-clockwise. Because minus you put anti-clockwise, again minus sign we should not write. Okay. Next, what is 176? At C for the member CB. At C for the member CB 176 kilonewton meter. Like that. So we have shown applied loads as well as end moments. Next, with opposite sign, we have to write the moments on the other half of the beam or frame. This is clockwise. When I fold it, it should be anti-clockwise. That I will show with other color. See, this is plus means minus 176 kilonewton meter. This you see minus 32 means here it should be plus 32 when you fold it. If this is plus 32, it should be minus 32. Here plus 16, that means it is minus 16 anti-clockwise. Now you see when I fold it, that clockwise becomes this way. That is called mirror reflection. Same thing when I turn it like this, it becomes this way. Okay. Same thing when I reverse it, this curve will come like this. Okay, 16 kilonewton meter. Now it's done. At C, let us see now. Plus 176 minus 176, when you join them already it became 0. If at all any moment exists here, who will balance that? So this value has to be 0. How to read it? Moment at C for the span CD must be 0. If this is 0, carry over moment also should be 0. Yeah, moment at D for the span DC also should be 0. So that's why at the axis of symmetry, columns will not be subjected to any moment. If at all there is any moment, when I fold it this clockwise, some values there say, how the symmetry will be there? So it has no choice. It has to be 0. Only then I can fold it without disturbing the, without having any slope. Okay. Now, this is one thing. Because it is first time, so I have drawn separately all the free body diagrams, then explained. Now it by inspection itself you can find y moment at C for the column CD. That they also know that you will find that moment at MCD is 5 seconds time. So they will ask you an extended question. That means this they will give plus 16, minus 16, 32, 176 they will give us. Then that means these values they give us. So time is saved. Then your question will be what is the axial force in the column CD? Such cases, quickly we must draw this free body diagram, applied load and moment. They have given these values. Now your task is this one. Due to applied loads, 24 into 8 down, so both supports will share. 24 into 4, 96, up, 96 up. Next, moments. Anti-clockwise 32, clockwise 176. What's the net moment? Clockwise only. How much? 176 minus 32 clockwise. So to balance it, anti-clockwise moment will, the couple will form like this. How much? What's the net moment? 176 minus 32 is the net moment, by length is 8. So you will get around this value. It works out to be 18. 18 down, here 18 up. Next, now final moment, final reaction how much? 96 plus 18. 114 upward. Because of the symmetry, here also there should be 114 only. Same thing, we don't have to repeat and waste our time. 114. Who will give this 114 kilonewton, 114 kilonewton to the beams? This column only should give like that. It should support them. If column will not give that much forces, beams will fall down. Now this column is exerting this much force on the beam so that they will be in equilibrium. That means what they are doing on this column is they are exerting a downward force like this. How much? 140, 228 down. To balance it, 228 up. Okay. So axial force in the member CD is 228 kilonewton. Moment at C means 5 seconds it will take, that it is 0. That they also know that you will find it in 5 seconds time. So extended question is this much. They give you the moments, find from the support reactions from the principle of superposition. That means this beam like a simply supported beam subjected to UDL, subjected to end moments. Strength of materials, many such problems you have done. Due to load, what is the reaction? Due to moment, what is the support reaction? Principle of superposition, add them. So this way what happens is clarity will be better. There is no way you can make mistakes because net moment is clockwise, so anti-clockwise couple should form. Here also same downward force will be there, 96 minus 18. How much it is, we are not interested in this one. We are interested only in this one. Okay. So one is up, one is down. Here both of them are upward. So like this. So what are your conclusions? At the axis of symmetry, always the column is subjected to axial force only, no moment. It behaves like a pure axially loaded member. Okay, that conclusions we will write. In this case, moment at in the column CD is 0. MCD is equal to 0, we have written. Then we will write as a generalized thing. At the axis of symmetry, bending moment in the column is always 0. Always 0. It behaves like an axially loaded member. An axially loaded member. So MCD is equal to 0, FCD is equal to 228 kilonewton compression. So this is one of the options they can give. MCD is 0 because it takes 5 seconds time. Another 1 minute FCD. So both they can ask what are MCD, FCD are. So 1 minute you should be able to complete. Now next question. This we remove. For the continuous beam, next question we are taking. For the continuous beam shown in figure, moment M is applied. Moment M is applied at B such that joint B does not rotate. Reaction at B is now this is the problem. This load here is 30 kilonewtons per meter. This point, let us say A, B, C. This is 4 meters I, 6 meters I. See here. So moment M is applied. There is a clockwise moment M is applied, so that giant B does not rotate. That means after application of the moment M, first load was there, theta B also will be there, theta C also will be there. Now you apply moment M so that theta B becomes 0. So after application of the moment M, theta B 0 means what? How the deflection profile will be? Always you, based on the description, try to draw the deflection profiles for all the problems. They will simplify your task. Okay. Now there is UDL and there is a moment M. A, B, C. theta b is 0 means after applying the moment m, how it might have deflected like this. Okay, this is your m. So that theta ba, theta bc must be 0. That is the question. So only deflection profile is like this. Now this deflection profile will tell you that this profile is like a fixed beam profile. A fixed beam, both ends fixed, let us say, their UDL is there, then fixed end moments also will develop. That profile is similar to this one. That means this deflection profile is a non-deflection profile. Then whatever things that you have studied about that deflection profile, simply attach them. Now we know what is the fixed end moment. Here how much it should develop for this profile. MFAB minus WL square by 12, 30 into 4 square by 12. That means minus 40. MFBA plus 40. So fixed end moment must be 40. Otherwise slope will not be 0. Slope is 0 implies that your applied moment is like a fixed end moment. Otherwise why slope will be 0? So your M must be 40. Here also MAB it must be 40. Otherwise slope will not be 0. Here also slope will not be 0. Once this is straight line, if at all it rotates, let us say, then some moment should be required to rotate it. It's not rotating means you didn't apply any moment, so rotation is not happening, because if at all fixed support is there, then naturally whatever moment you apply, then slope will be 0. It is not a fixed support rigid joint. At a rigid joint on the member BC, slope is 0 means we didn't apply any moment at all. If at all any moment you apply, however small it is, then rotation will happen. So MCB is 0 or MBC is 0, CB is also 0. So for this profile, the reactions are like this. We know what is the reaction here, WL by 2. Here also same thing. VA is WL by 2. W 30. 30 into 4 by 2. 60. VA is 60. VB is also same. VB is also WL by 2. 60. Then what is VC? In case they ask you VC, say it has to be 0. MBC also has to be 0. Moment at B for the span BC must be 0. Because theta BC is 0. Because no load is there. And there is no load on BC. That's the reason why MBC has to be 0. If at all load is there, theta is 0 say, then MBC will exist. Load is not there, theta is 0, that means moment has to be 0. Two reasons that why slope MBC is 0. There is no load on this one. Okay, so your conclusion. Your line of thinking must be like this. After applying moment M, theta BA is equal to theta BC is equal to 0. Okay, it means that joint B behaves like a fixed support, and M behaves like a fixed end moment. So once you understand that theta 0 means it's like a fixed end moment formula we know, then reactions are WL by 2. And these things are valid when no load is here. If load is also here, say, then we know how to calculate by using MDM. We will do that process, but it will take more than 2 minutes time. So they don't give two spans. I mean, load on two spans. Okay. Supposing that now this is about MDM, all the things we have taken. Sometimes what will happen is due to some reason, not because of the applied loads, the supports will sink. Supports will sink because of the soil problems. Due to strength of the soil is less, or due to the water level increases, then or liquefaction of soil, whatever may be the reason, if the strength of the soil is reduced due to water level increase or liquefaction, and whatever columns are there, they go down. When they are going down, they pull the beams also with that. If you have a statically determinate beam, when the support is moving down, no reactions, no movements will develop, because in a statically determinate beam, sinking of support causes rigid body rotation or rigid body translation. So no reactions will develop. But if you have a statically indeterminate structure like a fixed beam or propped cantilever, if any one of the support sinks down, then and reactions will develop, because there are more reactions than the equations of equilibrium. So those reactions will constrain the beam, will not permit rigid body rotation or rigid body translation to take place. Because they don't permit rigid body rotation to take place, they make the slopes zero by applying some moments. So some support reactions will develop to make the uh, slopes to happen, to make the slopes zero. Such cases where in the statically indeterminate structures, sinking of support, temperature changes, or yielding of support, or the lack of fit, they produce some additional reactions in the structure. So now, due to sinking of supports, how the frames behave, if we know, then those sinking effects also we can incorporate in the design. Okay, that sinking of supports, how they what reactions, what fixed end moments, etc., will develop in the frames, we will see.